Alright, so in this video I'm gonna be explaining another important article on model editing with the title Interpreting Graph Neural Networks for NLP with Differentiable Edge Masking. This paper in ICLR. Graph neural networks have become a popular approach to integrating structural inductive biases into NLP. Of course, after reading about more than 300 papers on GNNs and graph representation, I realized that there are 10 fundamental problems of graph neural networks, such as over-smoothing, over-squashing, lack of having good positional encoder, and so on. Robustness issue, overfitting, many issues, but we can still use it and modify and develop it. I mean, there are some ideas, and but we want to integrate it into NLP models. However, there has been a little work on interpreting them, and specifically on understanding which parts of the graphs contribute to a prediction. In this work, we introduce a post hoc method for interpreting the predictions of GNNs, which identifies unnecessary edges. Given a trained GNN model, we learn a simple classifier that for every edge in every layer predicts if that edge can be dropped. We demonstrate that such a classifier can be trained in a fully differentiable fashion, employing stochastic gates and encouraging sparsity through the expected zero norm. And so we use our technique as an attribution method to analyze GNN for two tasks: question answering and semantic role labeling, providing insights into the information flow. One of my works is a combination of using GNN and hierarchical pooling for natural language processing, but the ACL conference is maybe they only like ChatGPT articles and LLM. I don't know. So while GNNs often yield strong performance, such models are complex, and it can be difficult to understand the reasoning behind their predictions. For NLP practitioners, it is highly desirable to know which linguistic information a given model encodes and how that encoding happens. The difficulty in interpreting GNNs represent a barrier to such analysis. So this is the graph mask that uses hidden states and messages at layer K as input to a classifier G, and that predicts a mask Z. We use this to mask the messages of K's layer and recompute the forward pass with modified node states. The classifier G is trained to mask as many hidden states as possible without changing the output of the gated model. So a simple way to perform interpretation is to use eraser search. I think it was previous video that I talked. And the removal guarantees that all information about discarded features is ignored by the model. So eraser search would involve searching for the largest subgraph, which can be completely discarded. Besides faithfulness, considerations, and conceptual simplicity, discrete attributions would also simplify the comparison and relevance between paths. So, in eraser search, optimization happens individually for each example. This can result in a form of overfitting where even non-superfluous edges are aggressively pruned because a similar prediction could be made using an alternative, smaller subgraph. We refer to this problem as hindsight bias. So graph neural network messages, we aggregate and update, but it has locality problems, many problems, of course. That's why people develop next generations of graph neural networks. But here our goal is to detect which edges at layer K can be ignored. There are many papers like drop edge, drop message. There are many of them, but drop message is more general. It unifies all of these dropping methods. Of course, they use it for over-smoothing problem. But so it's very common to work on these things. So we want to detect which edges can be ignored without affecting model predictions. We refer to these edges and corresponding messages as superfluous. GNNs can highly sensitive to change in the graph structure. A GNN trained on graphs where all vertices have degree greater than n for some integer may become unstable if applied to graph where some vertices have degree less than n, very, very smaller than n. Hence, dropping edges without affecting prediction can be difficult. Nevertheless, many edges in the graph may be superfluous for all purposes other than normalization. Therefore, it is not enough to search for edges which can be dropped. Instead, we search for edges which, through a binary choice, can be replaced with a learned baseline. Conceptually, the search for a subset that generates a prediction can be understood as a form of subset erase. Okay, so to overcome these issues, we compute Z through a simple function learned once for every task across data points. So instead of selecting gate value Z here individually for each prediction, the parameters are trying multiple data points and used to explain predictions for examples unseen in training phase. Moreover, each Z is computed relying only on information also available to the original model when computing the corresponding GNN method. After G is trained to analyze a data point with graph mask, we first execute the original model over the data point to obtain H and M. We then compute gates for every edge at every layer and execute a sparsified version of the model. You see a toy example that we have integrated gradients, information, bottleneck, different methods, but this paper's method is amortized. And you see 0 and 1, 0 and 1. And for parameter estimation, we want to minimize, of course, the number of non-zeros predicted by G. So it's minimized by L0 norm, which is the total number of edges that are not masked. You see, like previous video, we still used this divergence measure to see how much the two outputs differ. So you see same idea you see in different papers. That's the idea. We first derive a representation of an edge at layer K simply through concatenation. We then compute scalar location parameters for the hard concrete distribution. So this is layer normalization here. So everything is standard. So we compute an alternative matrix form like gamma hat and we sample relation-specific matrix form and apply using an alternative to derive a representation matrix for the vertices in the masked model. And J here is just the all-one matrix. For the synthetic task, we employ a model consisting of one layer RGCN. This is relational GCN because sometimes there is a relation between two nodes. Why not encoding that? So instead of GCN, we use RGCN. And of course, all of these RGCN graph attention networks, they add complexity. It take more time than simple GCN, but they are more accurate. So there is a trade-off between accuracy and the time complexity.